Welcome back to a tutorial on circuit theory, and in this tutorial video we're going to learn how to solve a network using the maximum power transfer theorem. Okay, so before we go on to the details over here, let's just bring up the problem statement. Okay, so here's our problem statement concerned. Alright, so this says that, for the circuit provided alongside, calculate the value of R. Okay, so let's find R. Okay, so here's R. Okay, so it's one of the resistors in the resistive circuit over here. Okay, so we need to find the value of R if it should dissipate maximum power. Okay, so now we gotta apply the maximum power transfer theorem, okay, and whatever it says, okay, in order to calculate the value of R. We'll shortly just see how we should do that. Okay, so also we need to find the maximum power dissipated in this resistor R over here. Okay, so let's not just wait over here. Let's just quickly move on to solving this network. Okay, so let me just tell you a bit. Now that you've gone through the various principles of Thevenin's theorem, Norton's theorem, and the all other network theorems that you've come across, so I think you'll have kind of developed a sort of idea as to how to solve and handle these problems over here. So over here we need to in order to apply the maximum transfer power transfer theorem, we need to shorten or rather reduce this network over here. So if we just treat this resistor arm R as our as our load resistor arm, then in that case let's just name these terminals as, let's say, okay, I'll just call them A and B over here. Okay, that's better. So if we just take a look to the left of the terminals A and B over here in this circuit, okay, we can see that there are a lot of resistors, and then there's a voltage source far away from that of R. Okay, so in order to simplify the things over here, if we can go forward and apply the Thevenin's theorem, I think that would be quite a great deal of work over here. So in as far as simplifying things is concerned. So okay, so let's just go forward and apply the Thevenin's theorem. So before we do that, we need to reduce the circuit over here. So we need to calculate the internal resistance of the circuit. So let's just extract this part of the network. Okay, so here we have already extracted the part of the network on the left of the terminals A and B. Okay, so that's the figure on the left, as you can see over here. Okay, let's just label these points as A and B over here. Okay, so what we gotta find out over here, if we need to reduce the left part of this network by Thevenin's theorem, then in that case we just need to find the value of the open circuit voltage that would occur across the open terminals AB over here. So let's just name them as VAB. Okay, that's better. Now what we need to do is that we need to calculate the value of VAB right over here. So let's just pull the page down a bit. Okay, that's better. So in order to calculate that, we need to first see that this 5 ohms resistor right over here, this one I'm talking about, this is just open. Okay, so in such a type of circuit over here as we have right here, okay, so the current coming out from the 10-volt source would only circulate in this particular loop. So let's just call this as I, no problem. So now that the current won't go into the 5 ohms resistor, so we can pretty well understand that the voltage drops across these two nodes. Let's just call them X and Y. So the voltage drops across that of the node at the node X and at the node A are both the same. So in that case, let's just find out the voltage drop across the X and Y nodes over here. So in order to do that, we'll just find the current I first. So here we go. I is equals to 10 volts divided by the sum of these two resistances. Okay, so that comes to 10 divided by 30. So let's just keep it that way, or rather okay, I'll just reduce it over here. That comes to 1/3 amps. Okay, that's good. And now well, we need to find the voltage drop occurring across the 10 ohms resistor. So that's exactly what VAB would be. So here VAB would be equals to, well, VXY. So that's the voltage drop across the terminals XY over here. So in order to do that, we'll just, well, multiply the current I with the 10 ohms resistor over here. So current I is actually 1/3 of an amp, and that's multiplied with 10. So we get 10 by 3 amps. So that's equal to, well, about, let's say, 3.33 amps. Okay, so that's our value for sorry there, extremely sorry over there, it won't be amps, it'll be volts. Okay, so that's 3.33 volts. So we're basically going to get, well, 3.33 volts as, well, the voltage drop across that of the terminals A and B. Okay, so that's exactly what we needed to find. That's our open circuit voltage over here, or rather we can also, well, call it the Thevenin's voltage. That's what we're going to get for the reduced network over there. Okay, so now that we have found out the value of VTH, we have one more thing to do. Now we need to find the internal resistance of this left part of this network. I mean on the figure, I mean the figure on the left over here. Okay, so let's just go forward and do it. Let's just pull the page down a bit. Okay, that's better. All right. Okay, so there you go. So here's our the left part of the network with the voltage source removed, since we need to find the equivalent internal resistance of this particular network over here. So if we just go forward and look towards the network from the open ends, then in that way we can see, well, the 5 ohms resistor is basically in series with the parallel combination of the 20 and the 10 ohms resistor. So if we just go forward and compare it with the original circuit over here, you can see that this was the original figure which we got, and now we have just removed this source over here. Okay, just try to think in that way. So what the circuit would look like after removing the source. So here, this is what you should get. Okay, so in that case, the equivalent resistance, or let's just call it the internal resistance, R int, that would be equals to, well, 5 ohms plus that of, well, 20 parallel to 10. Okay, so that's going to be our combination over here. So if we just go forward and calculate the same, then we're supposed to get about, well, we're supposed to get about 35 by 3 ohms. So that would be well, expressed in decimals as, well, 11.67 ohms that we should get for the internal resistance. So that's our value over here. So now if we just go forward and, well, make the Thevenin network over here. Okay, so that's our well, reduced Thevenin's equivalent network for the left part of the circuit. And now if we just, well, go forward and, well, connect the resistance R right over here to the left part of the circuit, then in that case, well, the reduced Thevenin's network should look something like this, as you can see over here. Well, so that's our, you know, simplified network of the original circuit that's right over here. Okay, so we just reduce the left part and turn the circuit to something like this. Okay, so now this just, well, makes it easier for us to calculate the well, the you know, the value of this particular resistance, I mean the resistor R over here, and its power dissipation as well. So if you'll just kindly well, stress your mind a little bit to remember the statement of the maximum power transfer theorem, which states that, well, the value of the resistor, if it's supposed to, well, dissipate maximum power, should be equal to the internal resistance of the electrical network that it's been, well, connected to. So that's the exact reason why we just did this using the Thevenin's theorem. So over here we can see that the internal resistance of the network is, of course, given by, well, actually the value is about, well, 11.67 ohms approximately. So if the resistor R is supposed to dissipate maximum power, so I'll just write down over here for, well, maximum, let's write it in full over here. So for maximum power transfer, okay, so that's exactly what I'm going to write over here. So that's for maximum power transfer, the condition that should be, well, followed over here is that, well, R internal must be equals to, well, R. That's it. So this would be the condition for maximum power transfer. So in order to find out, as the problem statement says here, so calculate the value of R if it should dissipate maximum power. So in that case, just keeping that in mind, we can well understand that the value of R should be nothing but equals to about 11.67 ohms, which is the same as that of the internal resistance's value that we have just obtained shortly before, or right over here. Okay, so now that we know the value of the resistor R over here, I'll just write it down over here. So that's equals to 11.67 ohms. Okay, so now that we know the value of R over here, we can well go forward and calculate the amount of power dissipation that occurs across it. So we need to first find the value of the current I that should flow through the resistor R. Okay, so let's just call this one as I dashed. Very good. So the I dashed's value would be obtained as VTH divided by R internal plus that of R. So we're going to get something like 3.33 divided by the summation of, or rather let's just multiply it with 2, so 11.67. okay, and that's going to give us something like about 0.143 amps of current, okay, that should flow through the resistor R. Okay, so let's just pull the page down a bit. Okay, so that's better. Yeah, let's just keep it this way so that you can see the diagram as well. And now if we need to find out the power dissipation across that of R, so we can just write over here. So that's gonna be I'll just write it down as PR. Okay, that's the power dissipation across it, would be given as I dashed square R. Okay, so now if we just put the value of the current that's flowing through it, through the resistor R, so that's 0.143. okay, that's better, 0.143 amps. Let's just take the square of it and multiply it with 11.67 ohms, and that will yield us a result of about 0.238 watts approximately. Okay, and we could just also write it down as 238 milliwatts. Okay, so that's exactly what the power dissipation is going to be for the resistor R if we were to, or rather if it were to dissipate maximum power, and that's given by the maximum power transfer theorem. So for all kinds of problems on this particular theorem, you'll basically find situations like this one and something like the others as well, where you'd be frequently be required to reduce the network using the Thevenin's theorem. Okay, so that you can find the necessary values for the for either the internal resistor or the resistance over there, or rather for different purposes of finding out the power dissipation that would occur across the required resistor or arm that's as mentioned in the problem statement. Okay, so that's just brings us to the end of our tutorial discussion on this mathematical problem solving on the maximum power transfer theorem. So it'll just be all for now, and let's just see you in the next tutorial. And it's just a short goodbye for now, and thanks for watching.